Well, hello, everybody. Welcome to this another green energy series where it's presented by Solar Oregon. In this green energy series, we're going to be talking about community resiliency and specifically talk about how microgrids and resilient buildings can together result in a resilient community microgrid. Here. For those who don't know, Solar Oregon is a Oregon nonprofit that has been around for 45 years. The nonprofit's goals is education and outreach, community and advocacy. Some of the activities we do is we help give and deliver how to go solar plus storage webinars. We also organize solar tours. We do solarized campaigns, and we do peer-to-peer education. You can support our work by clicking on this link. And some of the upcoming events we have is on June 4th, there is a How to Go to Solar Plus Storage webinar. On June 6th, we have the Chief Sustainability Officer at Portland Public School deliver a webinar talking about Portland Public Schools' solar power efforts. I really look forward to that presentation. And then on June 11th, a company that does solar tracking solar panels will present on their technology. So that's a really cool presentation I also look forward to. This presentation will be presented by Zach. He is a senior engineering consultant at Mayfield Renewables. He used to work for Solar Oregon, and now he's working at Mayfield, and we'll have an opportunity to learn about some of the projects that he's working on now. And so for now, we'll switch over to Zach and give him control over the screen, and we look forward to hearing his presentation.
Awesome. Thanks, Edward. I'm going to go ahead and share my whole desktop here and jump into my slides. Thanks for having me. It's cool to be part of this series. I know you've been doing this series for a while, the Green Energy series. And yeah, it's great to be invited back by Solar Oregon to talk a little bit. Solar Oregon was certainly a chapter of my life. So I'm Zach Snyder. I am at Mayfield Renewables, as Edward mentioned, and I'm going to be talking about community resilience shelters. So what is a community resilience shelter? A community resilience shelter, I would say, is an idea that is moving toward implementation. And I'll tell you what I mean by that in a second. So what is this idea? It's based on the notion that there's a problem. And that problem is that the power goes out sometimes for whole communities all at a time. And sometimes that just happens randomly, but oftentimes it's associated with some kind of inclement weather, like severe winter weather, a heat dome event, or maybe associated with an earthquake. We do have the Cascadia seismic hazard here in Oregon. And the idea is that in that kind of situation, not only do folks in that community lose power, but they have to face, heating their homes or cooling their homes, or it may be a situation when they particularly want to communicate. So this idea is that why don't we have a community facility, say a public facility, a library or a school or a community center, where folks can go and during one of these kinds of events when they've lost power and go, get heat or cooling and use their cell phones to communicate with loved ones or charge a laptop and do some work. Maybe it can help with communications for folks who are trying to address any kind of, disaster kind of situation that's going on. So that's the idea. And the reason I say that it's an idea moving toward implementation is, to my knowledge, there aren't community resilience shelters that exist, strictly speaking. But this is something that came together. There's been a lot of climate legislation at the state level and the federal level since, I would say, 2019. And there's a lot of focus on how to uh, uh, implement and deploy renewable energy. And in a lot of this legislation over the past few years, this idea has kind of coalesced where, hey, you can deploy renewable energy. So in this case, right, we're saying solar plus a battery at a commercial facility. You can deploy renewable energy, and you can also solve these other problems, being, these community needs when the power goes out. And so that has wound up in a lot of legislation and a lot of grants, a lot of money is being given for this kind of idea. And so on the screenshot on the right is just some of the language from the Oregon grant program called the Community Renewable Energy Grant Program. And you can see it's a $50 million fund going to provide planning and developing grants for community renewable energy and for energy resilience projects. And so this idea of community energy resilience, that is this community resilience shelter. And, oh, excuse me. And so it's on its way toward implementation. I work at a company called Mayfield Renewables. We're a technical consultancy, and we engineer a lot of commercial size microgrids. We do a range of things, but this is a particular portion of the solar market you might be familiar with, and maybe you even have, or someone who has like a Tesla Powerwall or another battery and some solar at their home. And they can power a part of their home or maybe even all of their home during an outage, then this is moving that general concept up to the commercial scale. I, in particular, have worked developing our microgrid feasibility service, where we go and take a look. Often it's grant funded. So this service, is responding to a lot of demand as a lot of these grant programs have been implemented. To take a look at, okay, well, what is feasible for one of these community resilience shelters? So I have this special little window into what this idea that came about that's on its way toward implementation. And so I'm going to talk about community resilience shelters. I'm going to talk a little bit about community scale microgrids and how they differ, maybe say from what you might be familiar with if you are with residential scale. And I'm going to talk about feasibility studies and how we do that and go through a case study. And I want to frame all of this with in the context of, okay, we have an idea going toward implementation. And the question that arises is, okay, is this a good idea? And I think it's a question that should be asked every time you take an idea from idea space into implementation space. And so I'm not really going to suggest an answer to this question. I'm just going to talk about community microgrids, but I want to frame this in this question because I think it's an interesting one. So I have this little quote here at the bottom. In theory, theory and practice are the same. In practice, they are not. Albert Einstein. And so let's jump into it. What are commercial scale microgrids, right? Because this is not a home, this is a commercial facility. And they differ from smaller scale, battery backup for a home in a few different ways. One is that we're looking at a variety of different facility types. And so I mentioned schools, libraries, community centers, and there's going to be different ways that people interact with these facilities, different ways that people use energy, different equipment in the facilities. There's going to be a variety of different electric service types. So most residences just have single phase service. And when you're designing a solar and battery system, that has to be taken into account. And so in a commercial facility, you might have single phase, you might have three phase. It might be, 208 or 480. And so there's a little bit more variability in terms of the infrastructure. In addition, in commercial facilities, you just have a bigger building, and so load centers are far apart. You might have the utility service coming in, and it goes to a main switchboard, which is not something you would have in your house. It's a big electrical cabinet, and then that goes and feeds a lot of breaker boxes, which might be all over, might feed other big switchboards, depending on the size of the facility. But there's this larger kind of network of infrastructure. And maybe you want to back up, loads that are over here and over there. And you have to think about that when you're designing this kind of system. Additionally, commercial microgrids for commercial facilities, you're going to have different ways because of the scale of the building and also the use case of what they do there, different scale and types of heating infrastructure. So you might have big HVAC equipment up on the roof with big motors in it. You might have a big walk-in refrigerator or freezer. You might have specialized equipment loads, say at a hospital where you've got testing and laboratory equipment and imaging equipment. These can add some complexities, for example, around surge current. And that's just, when a big motor turns on or there's a transformer, it just has a big spike just momentarily in the electricity. And your inverter for your microgrid system has to be able to handle that. There might also be existing generation equipment. Commercial scale, often you'll be using more electricity as a whole in the facility. And so that opens up some opportunities around economic battery dispatch, because where there are demand charges on the utility bill and you have high demand, you might be able to reduce your utility bill a lot just by tamping down those peaks on your bill. And that might be much more effective for commercial than for residential. And last but not least, there's just the human element. And, for a home, typically there's, a family. It's relatively easy to make a decision about what to do with the home, although not always. But for a larger facility, for a school, you might have a school board that needs to be the one making the decision about any infrastructure getting installed. It's just a little bit more complex. And so that changes how these are implemented as well. So given all of that, given this variability, with residential, if you're thinking about just a home with a battery and solar, that it's relatively productized, where you have a system that they have a lot of them and they're just, they do the same thing, and the homes are relatively similar. And so they're putting them out there. But I want to tell you some of the functions that these things do in that, container. And there are multiple functions that a microgrid may have to perform. And those can be not a one size fits all when you go into the commercial space. So for example, when the grid goes down and you still want to use power in your facility, you can't have any of that power going back out on the grid. That could endanger utility workers working on the line. So your system has to be able to island, to be able to disconnect electrically from the grid. Additionally, you may have a system where you want to back up a lot of loads, but you're not sure that all those loads can be backed up for the entire duration of the outage. And so at some point, you might want to shed some of those loads. And that's something that needs to be taken into account in the design. With larger systems, there might be an existing generator, or maybe it just makes sense to put a generator on a commercial scale microgrid. And there's generator integration to worry about. If you want to take advantage of what I was talking about earlier, where you are reducing the peak demand and reducing your demand charges on your utility bill, your microgrid has to know that it's going to do that, and it has to be programmed so that it is able to do that. And it might require special metering equipment that you have to think about. And so in addition, there's just other aspects of how the system is doing typical maintenance of itself. The battery needs to cycle every once in a while, even when there's not a grid outage, in order to maintain its lifespan. It's actually unhealthy for the battery to be full all the time. And your microgrid, you might want to, if you have a generator integrated, you might want to start that up every once in a while, because if it's sitting for a long time, that can create some issues when there is an outage and your generator doesn't start for you. It also needs to, batteries, they have, lithium batteries in particular, they have a tendency to be prone to fire. That is something that is, I think, a lot of effort is put into minimizing that. And there's also in all these battery containers going to be fire prevention and suppression measures. There's lots of testing to do with safety as well. But those are separate functions, as well as internal climate control. The battery just performs better, and it's healthier for the battery if it maintains a stable temperature. So that's just exploding out the complexity a little bit of all the things that your battery system for a battery-based microgrid that it might have to do. So what does this really look like for the commercial space? A lot of those functions are still integrated into a container, basically. And so here's a couple of examples of containerized products. They really vary in scale. You can see the one on the left is more of a shipping container size. The one on the right, I think a medium or small shipping container size. The one on the right is a bit smaller than that. But there are different sizes, but they do try to containerize and productize batteries for the commercial scale as much as possible. So I should say, in these containers, oftentimes you'll have the batteries, you'll have an inverter, which converts the DC power of the battery into the AC, so it can be exported to the grid. You'll also have, the HVAC and everything in here. You might also have a controller in here. However, sometimes you won't have a controller. The controller is what controls the dispatch and integration with solar and generator. And so in certain cases, you can rely on the controller in that container. However, sometimes you have to add an extra higher level controller if you need to perform certain functions, or you're trying to integrate certain technologies into your microgrid that are beyond the bit more basic capabilities of what might be in that controller that comes with the battery container. And so there are providers of controls. These are things that are usually programmed, sometimes individually, sometimes it's a little bit less on a case-by-case basis. There's a little bit of a range, but these can perform very complex functions when that is needed. And then there are also times when you're going to want to use additional equipment here. I'm trying not to get too much into the weeds, but on the left, there is something called a contactor, which is basically an electric switch. And this is useful for load shedding. Maybe you have some loads backed up over here, some loads backed up over here, and in the middle, you have an electric switch, and your controller, your brain for your microgrid, can know, oh, when I'm this low on battery, I can break that switch, and then these loads stop receiving power. That's one way to do that. This is also used for grid islanding. On the right is just a manual snippet from a really commonly used device called an SEL relay. These are used all over the grid. They're kind of the Swiss Army knife of the grid, I would say, in a lot of ways. They can perform metering functions as well as islanding and things like that. So that's a little bit of the basics of community microgrids. I don't know if I mentioned, I'm using a lot of AI generated imagery. I thought I'd test it out. I actually really like it so far for this presentation. I'd be curious to see what you think. But this is, you can see that AI doesn't always spell super well. So this is feasibility studies is what I will be talking about next. Okay, so those are the peculiarities of commercial scale microgrids, which are essential to the concept of community resilience shelters. So what is a feasibility study? What do we do when we take a look at, what is feasible? We are, they're called feasibility studies, but really you could call them optimization studies in a lot of ways. we're trying to determine the optimal architecture. And so that's the components and how they're connected. And we're trying to estimate the performance. And so when you're looking at a community resilience shelter, one thing you're really thinking about is how long can this system endure a grid outage, right? If the power goes out at this time of the year or at this time of the year, what does that actually look like? So that's something we try to do some energy modeling and characterize that. And we also do some financial modeling and characterize the quality of the investment. As I mentioned, there are grant resources for these kinds of things. Sometimes these are privately funded. For community resilience shelters, I think they're particularly grant funded. But there are lots of commercial scale microgrids that go in that are not grant funded. So so what does this entail? So I think of this conceptually in 4 kinds of steps of a feasibility study. The first step is where we discover how much of the human component this is. I call it the discovery process, and we do some interviews of stakeholders, the people who use and run and own the facility, people doing this project, and we see, what are your goals? What are you trying to accomplish? How long do you need power during an outage? How is your facility used? How do you envision people using the facility during a grid outage? We do some data collection. So we ask for existing building drawings. Electrical drawings are really useful to be able to take a look at the how the building's electrical infrastructure is laid out. We do data collection sometimes with a site visit, or we go and sometimes place a meter to get really granular data of how they're using power at that site. And then we take all this information from the discovery process, and we sit down and we analyze it and we prepare it. And what we're trying to do is identify constraints, because there's going to be some constraints. Sometimes that's budget. Sometimes that's the existing electrical system. Sometimes that's, do you have space for the microgrid equipment, the batteries and the solar? Sometimes there's, regulations that apply for this particular type of facility, or there's just the desires of the project group. Then after we've identified those constraints, we sit down and we do our preliminary technical analysis. And this involves both the energy and financial modeling I was talking about, but at the same time, we have a design engineer who is designing the actual architecture of the system. And these are happening in conversation with one another. And so we do some modeling, we do some design, and we're working towards the optimal architecture. And then we present this to the client. And this is, I think, one of the biggest aspects of a feasibility study is the communication with the client, showing the client, okay, here's what we've determined might be the optimal system for you. Now that you can see it in front of you, what do you think? And when people can see, okay, here's where the solar is, here's where the battery is, here's the performance, here's the constraints and construction hurdles, they get a lot of ideas. And there's often a lot of work to do to meet between what is in people's minds and what the engineering reality is. And so that happens through this review process and these conversations. We update the analysis and deliver a feasibility study. And that's how we do that. So here's just a little image of one of the meters that we might place on site to record electricity and get that really granular data that helps us with our analysis sometimes, mostly just for fun. So, all right, so that's the basics of a feasibility study. And now I want to talk about a case study. So I selected this particular project because I think it's representative of what a lot of people will think of when they think of community resilience shelter, as well as typically what you might find and some constraints that might be encountered. So this is a site that's in Oregon. It's a rural school. And the project goals for this site are, okay, well, we, in the summer, we have wildfires around us in the area, and sometimes in the past, and we expect in the future. Maybe we want this to be a command center for wildland firefighters. And that can happen for a couple of weeks at a time, sometimes longer. And then in the winter, there are a lot of severe winter storms, and when especially more elderly folks in the area lose power in their homes, it would be really nice for them to have a place for them to come. They know that there's going to be heat, because there's going to be this backup microgrid system that's going to be able to power the boilers in this case. And the goal was really, even then, you're probably going to want at least a week of resilience. So that's the goal. And this is a big facility. You can see there's a lot of different sections of it. And with the budget limitation, this is a grant project. With the budget limitation, the question is, how much can you power, and what are you going to select to power? What are the loads that you're going to select? That's often a really big conversation. And so in this case, some of the key loads were, they actually had a municipal water pump on site that helps to serve the entire area with water, not just this facility. And that was something. There's pumps and other loads related to that. There's also, obviously they want cooling in the summer. If it's, related to wildfires, it's probably going to be potentially kind of hot. You want warming in the winter. And so some of these, there was a HVAC system with boilers and other components. They want to be able to prepare food, and they had a kitchen, but there were actually a lot of appliances were not gas, they were electric. They were not induction electric, but they use a lot of electricity. So electric griddles, things like that. And there's a big walk-in refrigeration unit. There's also IT and server loads. You want to be able to use the internet. You want the heating and cooling to be able to communicate, because that requires the internet as well. And then you also maybe you want lights and receptacles so that in the dark, people can see where they're going, and people can plug in computers and cell phones and communicate like that. So the constraints, there's a lot of space here for solar. We actually decided in our analysis to put the solar as a ground mount. And there's plenty of space for battery here too. So that wasn't really a constraint, but there was a $1 million budget. And there's some complexity to the electrical system because there's 2 utility services in this building. So we just had to navigate that a little bit. And it's also an old building. And so there wasn't, one drawing set that we had that had all the information for the existing infrastructure. And there was a little bit of investigation that we had to do. So the first thing that we had to do then was load selection, and this is really where a lot of the focus was. And so this table I'm going to walk you through a little bit. It's a table of the loads that we are selecting for our analysis when we're doing energy and financial modeling. And so we have a set of loads. Think of each one of these corresponding to a breaker in a breaker box. And you'll see a priority. So they're ordered in their importance from 1 through 27. And you'll see their name. And you'll see we have scenarios 1, 2, 3, and 4. And then we have the amount of power for each of these loads. And so these scenarios, we're basically saying we're going to model 4 different scenarios. Say you want to choose all these loads on the list. There's not all the loads in the building, but all the loads on the list. That's the first one. Then we're going to cut off a few down here. We're going to cut off some of the unnecessary kitchen items. Scenario number 2 has everything else. And then scenario number 3, we're going to cut off some of the, additional unnecessary kitchen items. Scenario number 3 is got some basic refrigeration, the lighting and receptacles, and the heating, basically, and cooling of the facility. That's what you get in scenario 3. And it's really the heating and cooling in certain areas of the building. And then scenario number 4 is cutting out even the refrigeration. So you're going to let your food spoil, but you still get the heating and the cooling and the lights and receptacles. So there was a lot of triage. These were not all the loads that we wanted to look at. There was a longer list of loads, but this is after we kind of worked it down. This is what we ended up analyzing. So lots of triage involved. And there were some really important loads that we ended up wanting to remove because they were just too big, given the constraints of the project. So the water pump I mentioned got removed, and it was decided that would be handled in another way. Kitchen loads. Yeah, like I said, there's a lot of this where we're dropping things off successively. That happens in the kitchen. And we really just focused on core essential areas. So here is the quote unquote high level architecture of the system that we ended up analyzing and designing. And this involved 91.2 kW of ground mounted solar, as well as 276 kilowatt hours of battery system with a 250 kilowatt inverter. I know that's a lot of Ks and Ws and numbers. If this may be more or less meaningful to you, but this is just the size of the system, basically. And we did this and we performed energy and financial modeling based on this.
So for reference, a typical home has like 5 to 6 kW of solar, and then if you have
Yes.
a Tesla Powerwall, it's about 10 to 12 kW.
Exactly. Yeah. So when we're looking at, we're looking at these numbers. Yeah, this is 100, or this is 15 times, say, the size of the average Oregon home of solar, and then here might be 20 times the size of the a single Tesla Powerwall.
Exactly.
Yeah. Mm-hmm. All right. So this is often the chart that is going to occupy a lot of people's interest in the results of the study. We're looking at how long does this system that we specified last during a grid outage at different times of the year. And we're looking again at those 4 different load scenarios. Everything a little bit less, and the bare minimum. And so you'll see I'm going to walk you through this chart, the 4 bars. So first of all, the bottom of this chart is January through December, the 12 months. Each one of those months, you'll see the 4 bars. Purple is scenario 1, blue is scenario 2, scenario 3 is green, scenario 4 is red. It goes from the most loads to the least loads, left to right. And we're looking at the number of days that scenario is expected to last in each month. And so you'll notice that these bars in November through February, March are really small compared to the bars in May through August. And let me tell you what that means. So if you have load scenario 1, that means you're backing up, all the kitchen stuff that you wanted, and you got your heating and cooling and whatnot, and your refrigeration. You're gonna be in January. This is at 90% confidence. So there's a little bit of statistical variation here, but at 90% confidence, it might be as little as 5 hours of resilience in December and January. And so you have to ask yourself, what does that mean for my December folks? In June, July, August, when maybe you're going to have a wildfire. So that's the wildfire fighting time and different use case for the building. You're going to have, so this chart only goes up to 30 days, but basically if an outage in load scenario number 2, 3, or 4 starts in May, it's going to go for like 3 months, potentially all the way into August. So and the reason why this happens is that there is a point at which so when the grid goes down, there's so much energy in the battery, and then that starts to deplete. But the solar, if there's abundant solar that can recharge the battery, there's going to be some solar in the winter, but it's not going to recharge it all the way or really nearly as much as you're drawing energy down in the winter. But in the summer, that solar is going to be putting more energy into the battery, trying to put more energy into the battery every day than you're drawing out of it based on our load scenarios. And so what you get is this kind of runaway resilience effect in the summer, where you have great resilience in the summer, but then it dips down really low. And this is an inflection point. And so you need to figure out, how can I maximize, what are my use cases? And is this going to be useful for the winter? Is this going to be useful for the summer? These are the kinds of questions that come out of this. And so I'm not going to spend too much more time on this analysis here, but you can see that it raises a lot of questions. And so there's often a lot of information and conversation to be had from a microgrid feasibility study. Another activity that we do as part of our feasibility, we're not an installer, we don't install these systems, but we do have subject matter experts with construction experience that help us to develop rough order magnitude budgeting. And this is useful for example, applying for a grant. And so this is something we did for this project, and you can see we tallied up different costs based on materials for battery, for the solar. There's things like fencing that you have to think about, and shipping the materials to the site, renting heavy equipment for site preparation, the site preparation activities themselves, and the labor involved. All this, and then the engineering and administration of the project as well. All of this adds up. And so this project had an estimated capital expense of about $940,000. This is a rough order magnitude budget. Later, should be constrained by an installer that will actually can give pricing. But this is, so this is in looping this back into the concept of a community resilience shelter. The idea of community resilience shelter is we get these benefits, and it's a way to deploy renewable energy. And a lot of these projects are grant funded. If you were to install a generator that would give a similar level of performance, potentially even a better level of performance in the winter, though we didn't actually run that analysis for this project. It might be, and likely would be, less than $100,000 of capital expense. So looping this back to the idea of community resilience shelters, I'll just note, here's I think, some takeaways, and I'm going to focus on the challenges more because I'm coming from an engineering perspective, and that's what we do. The challenges include, renewables are intermittent. That's why you see this kind of runaway resilience effect in the summer, tons of abundant solar energy in the summer, but that's just not reliable necessarily in the winter, and you can't control that in a way that you could with, say, a generator. Load selection is often where we spend a lot of our time. So that's selecting which things do we want to back up, which breakers do I want to put in my microgrid, and that's really tough because people, when they're planning for a community resilience shelter, they're often planning for something that hasn't happened. Like their facility has not had power during an outage. They've not been able to provide this service of community resilience shelter. They don't know how people act. They don't know how people use energy. So a lot of it is kind of speculative. And there's a lot of conversation that happens around that. In terms of available equipment space, there are some projects that are very constrained in where you the amount of space for batteries and solar, that is solar can take some space if you really want a big project, and batteries do have setback requirements from buildings and from public ways for safety reasons. There's also available budget is a constraint, though obviously that's overcome to a certain degree with grant funding. And then there's utility interconnection requirements. So in some utilities, it gets more and more complex the larger solar system you want to interconnect. And then a big one, I think, for the challenge for the concept of community resilience shelter is The fact that, this is maybe one thing that a facility wants to do is to provide this resilience service to the community. They might also have goals with regard to electrification of their gas, heating and water heating and cooling infrastructure. That's going to increase the amount of electricity. That's going to reduce the amount of resilience in one of these events if you're including those loads in your backup loads. Same thing with EV charging. EV charging puts a lot of load on the building. And so the idea of being able to charge your car from a community resilience shelter seems really difficult. And then there's just thinking about, if this is a rural area, thinking about, who do you have who can service your facility, who's going to be available. There is some routine maintenance, some, battery products. It's an annual schedule that the manufacturer recommends. Some of them, it's a little bit more frequent even. And so that's just an aspect. So I know that that's a list of the challenges, but again, coming from an engineering perspective, that's what I think about all day. So that is my presentation on community resilience shelters. I'm looking forward to taking a look at some questions.
Wonderful, Zach. I have a particular question that comes into mind. One is it a acceptable design method to oversize your solar panels so that you overproduce during the summertime and potentially even waste a lot of that solar energy by putting the panels into open circuit once there's no longer a need for that energy? The batteries are already full. You maybe have even maxed out the amount you're allowed to send back to the grid in attempt to try to get more of that solar panel generation in the shoulder season, so like March and October, for example, so that you can have more hours during those periods. Has solar panels gotten so cheap to the point where it makes sense to design that way?
That's a really good question. In terms of so to answer technically, yes, the adding more solar is a strategy, and then you can curtail it. So if you say you're up against a utility interconnection limit, say you're up against 100 kW interconnection limit, which is common in the state of Washington, for example. I know we're in Oregon, but that's how much you can interconnect in terms of inverter capacity. You could have a DC coupled system, and there are limits to the amount of solar that you can connect to a certain, any given DC coupled inverter. So DC coupled means that both the solar and battery are behind the same inverter. So there's going to be a technical limit with the inverter. But you can also curtail the inverter capacity as well. You have to work with the utility.
Right, that's what I was thinking.
Yeah. Yes, you can, and that is sometimes a strategy that we've looked at for projects and recommended. In terms of the cost of solar being low enough to make that something where you could get a ton of performance in the winter, say at this kind of site. It really depends on the installation contractor and how much they want to charge per watt. It does vary a little bit from place to place and from contractor. There's a market, right, that sets the price, but some places are a little bit more expensive and some contractors may be slightly more expensive. But it's not I would say a silver bullet for that problem, but it's certainly an interesting strategy to look at.
Oh, excellent. Okay, there's another question in the Q&A, which is talking about solar systems being compared to a generator, like a gas generator, or natural gas generator, and how that's not a real fair comparison because you also have to talk about fuel cost and fuel maintenance. And for example, with natural gas, even if you don't use a single therm or a single cubic feet of natural gas, you're still paying those account fees each month. So can you comment on kind of the cost of a solar plus battery system versus generator and then all those ongoing maintenance and account fees socio and how that pans out over time?
Yeah, that's a great question. I can't address it definitively, just partially because the feasibility studies where we do these ROM budgeting, I have not priced out and done a multi-year analysis for generator because a lot of these are looking exclusively at renewables. However, you're right. There are fuel costs. There's the marginal cost there of the actual fuel that you're using. There's also you have to have a storage for say a propane generator. For natural gas, you have the natural gas grid. Sometimes you if you're rural, you want a propane generator. You also have to have a storage tank for that. There's maintenance as well for generators. I'm not sure how that stacks up, but I wish I could give a more definitive answer to that. But you're absolutely right. There are some costs there beyond just the capital costs.
Yeah. I know at my work at Pacific Northwest National Laboratory, we have staff that are trying to help Army bases all over the world upgrade their backup electrical systems. And they are seriously looking into solar plus storage as being a solution because the maintenance cost of generators is so high. Um,
Interesting. Yeah.
Okay. And then when you had the feasibility table of the breakdown in rough order of magnitude cost, which scenario in like the different amounts of backup, um, which scenario did you choose to run those numbers for?
So that's actually independent of which
Oh,
scenarios.
okay, it's independent.
The scenario chosen is going to impact the performance of it, but for all four scenarios, we modeled the exact same system architecture in terms of the amount of battery and the amount of. There's some small difference in cost based on the sizing of the backup aggregation panel, but it's going to be a couple of percent of the project cost at most.
Okay, cool. Um, so in this presentation, you articulated a kind of particular type of microgrid. We have a question here, kind of maybe if you can kind of speak more broadly about, the term microgrid and what it could mean to different people, and then maybe give that kind of 36,000 feet view of microgrids.
Yeah, that's a great question. That microgrid is a word, and people use it in different ways and to mean
Yeah.
different things. And so it is a great question. And it's a word I would say that's more exists in the ether, and then people co-opt it. So I think that the battery, solar and battery kind of backup situation has co-opted the word microgrid, and all sorts of different types of people have co-opted the word microgrid. It can mean a lot of different things, but I would say typically, if and I'm not necessarily an authority, and I'm not really sure who I would point to as an authority, honestly, on the word, um, because it has so many different meanings. But I think people think of multiple buildings or like a campus, typically in a kind of a classical way of thinking of microgrid. That's how I classically think of it. That's something that we do feasibility studies for that kind of thing. But we also tend to use the word when we're talking about a single building, a commercial building, a single, part of a school kind of thing, even. And but there are also microgrids that kind of stretch across like a medium voltage distribution system, whether that's utility owned or owned by a campus, like a university might have their own medium voltage distribution system. And so there is that aspect. We've done some projects up in Alaska on really remote grids. So these are very small communities of like 100 to 300 people up in kind of, I don't know how to describe exactly, but north, almost like right about at the Arctic line in Alaska. And up there, they don't have transmission lines running from, the main municipal areas. They have a generator house and they fly in or barge in diesel fuel. And then they have this generator house, and it powers a couple of radial distribution lines. And then, interconnecting battery and solar, it's a lot of battery and solar you're putting on there compared to the size of the grid. And then, that is kind of it's own, it's hard, you could call it a microgrid, you call it a grid, right?
Their grid is
Or
the size of a microgrid.
yeah, exactly.
Yeah.
So, yeah, there's a lot of different ways to look, different types of projects. So,
Yeah, so adding to Zach's kind of thoughts on microgrids, I think any section of the grid that you can section off so that it's safe to continue to run during an outage in other parts of the grid, if you can island that section of a grid, then you can consider that islanded section a microgrid. So like Portland General Electric, you might have heard in the news or in different media sources that they're doing microgrid studies. What they're really doing is like at the substation level and on their distribution system map, they look at where the different pieces of equipment are, where the switches that they can put additional switching gear in that location to be able to like island this neighborhood safely so that they are 100% sure that it won't backfeed power to other parts of the grid when it continues to run during an outage. So these types of things are being thought of at the utility, even though they have a much larger grid. They are interested in microgrids for community resiliency reasons, or that there's certain customers in that particular neighborhood or part of the distribution network that's really high value. Like for example, like a level 1 hospital might be worthwhile to microgrid that particular area just for that purpose. Yeah. So I don't see other questions here. Let me double check. I don't see other questions. In that case, what I want to do is do a plug for next green energy series that are coming up. And so I can take over the screen share and show you what those look like. Okay, share. Full screen. You able to see?
yeah, looks good.
Awesome. So we have a July 6th Green Energy Series teed up, and that is going to be presented by Doug. And Doug is a he's got a really unique PV system. It's think of a solar panel with a heat exchanger behind the solar panel. So it's both solar and thermal. And when you have solar panels in your roof, think of that panel as like, well, it gets hot. I mean, the fact that it's even on the roof on a sunny day means that by default it gets hot. And you might know that the efficiency of solar panels actually decreases a little bit as it gets really hot. Well, why not be able to capture some of that heat off the backside of those panels with some sort of thermal collector? Well, that's kind of the idea that Doug was going for. And so he has a system that can do that. And even in the summertime, a typical home has thermal loads. For example, domestic hot water. Like even in the summertime, you don't like to take cold showers. So even in the summertime, the thermal load is useful. And then, for example, if you have a climate zone where you get snow covered on your panels, well, maybe you can even run the system in reverse and snow melt the snow off your panels and then be able to produce some more electricity. These things are, I've got so many questions for Doug, but we'll get the chance to hear from him on July 6th. And then on August 3rd, Julie will talk about Seeds for the Soul, which is a peer-to-peer loan program that allows folks who don't really have the upfront cash in order to purchase a solar PV system, be able to do so with peer-to-peer loans. And depending on the economic conditions, as a peer, investing your money into a Seeds for the Soul loan might net you some better returns on investment than you could putting money in the bank, for example. So looking forward to hearing from Julie on August 3rd. Keep an eye out for emails on Eventbrite links for these next Green Energy series, and we look forward to people signing up for them.